Flying has been mankind's dream since the 8th century BC. Because of humanity's quest to fly, history is packed with countless attempts to outsmart gravity. On December 17, 1903, one attempt succeeded. One where the pilot laid on his stomach on the lower wing and controlled the flying machine through a cradle attached to his hips, navigating it through the air in all dimensions of flight: pitch, roll, and yaw. The attempt lasted just over 12 seconds, but when he landed, he and his brother cemented their place in history. Orville and Wilbur Wright had just invented the first successful powered airplane, sparking the golden age of air travel. But how did they succeed? The reason for their success was in the very interesting shape of the wings. The wings were curved upwards, forcing air to flow downwards. This is known as the airfoil technology. Sir Isaac Newton stated in his third law of motion that for every action there is an equal and opposite reaction. As the wing pushes air down, air must also push the wing up with equal force. This force is known as lift. When the lift generated exceeds the weight of the aircraft, the plane will take flight. Today's airplanes are still governed by the same principles of aerodynamics. They still utilize airfoil, but in a highly aerodynamically refined shape. Swiss mathematician Daniel Bernoulli stated that as the velocity of a fluid increases, the pressure exerted by the fluid decreases. When air travels over the top surface of the wing, it speeds up because of the steeper curve. Due to the speed increase, the pressure it exerts on the wing lessens, creating an area of low pressure above the wing. At the same time, pressure on the bottom of the wing is greater. The difference in pressure causes the upwards lift force. In other words, more speed equals less pressure on the wing, and in reverse, less speed equals more pressure on the wing. Make sense? You can test Bernoulli's awesome principle with the use of an oversized hairdryer and inflatable ball. The same rules apply here. Faster air on the top causes less pressure, while slower air on the bottom causes more pressure, lifting the ball up. Also, the continuous flow of air keeps the ball steady instead of blasting it out of the air. Both Newton's and Bernoulli's explanations on lift are true. They are simply two different ways of looking at the same thing. Increasing the angle of attack will produce more lift as the pressure difference between the top and bottom surface is much more greater than before. This explains why airplanes lift the nose during takeoff. They do this to direct more air to flow below the wing, greatly enhancing the lift. From then on, the plane will rise effortlessly to the sky. Airplanes also take off against the wind in order to get as much air as possible flowing across the wing. It gets a little confusing here, but lift is determined by the coefficient of lift, the air density, the velocity or speed of the aircraft, and finally the wing area. So for example, increasing the aircraft speed will result in a lift increase, same result if you increase the wing area, and so on. The graph is used to display the relationship between the angle of attack and the coefficient of lift. As the angle increases, lift is also increased accordingly up to its point of stall or critical angle, alpha crit. Basically, when the aircraft exceeds its critical angle, the plane stalls and falls out of the sky like a rock. In the experiment conducted, airflow can be seen represented by the ribbons on the wing. As mentioned earlier, when the angle of attack becomes greater, lift is increased, causing the plane to climb. However, if the angle becomes too great and reaches critical angle, air is restricted from flowing over the wing smoothly, causing an aerodynamic stall. Stalls can only be recovered from by lowering the nose to restore airflow and lift. Modern planes use flaps on the trailing edge, the back end, slats on the leading edge, the front end, and spoilers on the top surface of each wing in order to manipulate the shape of the wing. When flaps and slats are extended, they will increase the wing area and curvature of the airfoil, allowing for the aircraft to fly at lower airspeeds while maintaining lift, making it extremely useful for takeoffs and landings. On the other hand, spoilers, also known as lift dumpers, are used to reduce lift created by the wing upon landing to ensure that the plane touches down safely. Spoilers can also be used to increase the drag to help the aircraft slow down. Once armed, they extend automatically and force all of the aircraft's weight onto the landing gear, making the brakes more effective while slowing down. An interesting phenomenon of physics occurs at the cruising altitudes of jetliners. The atmosphere is 10 times thinner at 40,000 feet than on sea level. Aircrafts must maintain a higher airspeed due to the rarity of air in order for the wing to provide the same amount of lift as it would at sea level. This isn't a disadvantage, as a thinner atmosphere means less drag, so an aircraft can fly at high airspeeds while burning the least amount of fuel. However, pilots must be cautious as not to climb too high to the point where stalling meets overspeeding. This deadly region is known as coffin corner or the aerodynamic ceiling, and the only way to keep the flight safe is to descend to a lower altitude. Humans have tried to fly for more than 2,000 years. Think about this the next time you're looking out the window of an airplane. And remember, 2 wrongs don't make a right, but 2 rights did make an airplane. Thanks for watching.